starting from now, we want to start looking at the other half of calculus. Remember, I was saying before that calculus really has two branches to it, right? It has an instantaneous branch and a cumulative branch, right? The derivative, this looks at an instantaneous rate of change, right? It looks at, here's a function at this specific value. How fast is the function changing, right? To get to the other half of calculus, the cumulative part, we want to sort of first start by thinking of, all right, how do I undo a derivative, right? And these are what we're going to call antiderivatives. So let's start with something like this. Let's say we have a function f of x. We want to find a function f of x such that the derivative of capital F of x is little f of x, right? So again, we're really looking to undo a derivative here. So if we just pick an example here, like let's say f of x, let's do something a bit simple. Let's do 2x cubed. Okay. So let's say I have this function here, and I want to find an antiderivative of it. Okay. So what kind of a function would give me the derivative 2x cubed? Okay. So to figure that out, let's think about how, what kind of a derivative could have an x cubed in it. Well, if we think about the power rule, we know that the derivative of x to the fourth is 4x cubed. But this is a little bit different from what we have, right? It's a factor of 2 above what we actually want. So if we sort of imagine multiplying both sides of this equation here by a half, well, remember we can factor constants out of a derivative, and in the same way we can put a constant back inside of it, right? So we have the derivative of 1/2 x to the fourth. That would be 2x cubed, right? So an antiderivative could be f of x equals 2x cubed. Oops, sorry. That's what we're trying to find the antiderivative of. Sorry, 1/2 x to the fourth. Right? So if I find the derivative of this, f prime of x, I'm going to get back to what I started with, 2x cubed. Right? But let's think about this some more. What if I picked f of x equals 1/2 x to the fourth minus 5? Right? Let me put a little 1 here. Right? Then, well, f prime of x is still going to be 2x cubed. If I pick f2 of x to be 1/2 x to the fourth plus 1,000, right? F prime is still 2x cubed, right? And you can imagine I could add or I could subtract any number, any constant I want, and my derivative is still going to be 2x cubed. So, we can find many different antiderivatives of a function, right? And they all differ by some constant here, right? So what we'd like to do is kind of summarize that all together and say, all right, here's a function. What's sort of the most general antiderivative I could write down? What's an antiderivative that somehow captures every possibility? Right? So that's what we're going to call sort of the general antiderivative. right? And what we're going to do here, so this is what we're really going to call f of x. And that 1/2 x to the fourth part, that was really important. The other part here, we're just going to say plus c. Okay? And this plus c here, this thing, is what we call an arbitrary constant. Right? So this c here, we can put any number we want there. And since we can put any number we want there, we're just going to call it c. Because, well, it doesn't matter. Right? It's important that it be there because, again, all of these options here, they're all antiderivatives, no matter what number we fill in. But we don't want to specify a particular number. We want to keep it as general as possible. Right? And that is the idea behind an antiderivative. Before concluding this, though, I almost forgot here. What are the differences between all these different values? Right? What does that arbitrary constant c stand for? So let me write down sort of graphically what this is. Right? So I'm going to give sort of a sketch of what this could be. Okay? So graphically, right? So let's say we put in blue 1/2 x to the fourth. Now I'm not going to attempt to put this to scale or anything, but 1/2 x to the fourth is something like this. Let's use this one. 1/2 x to the fourth. Right? So what does that constant do? Well, if we start adding values to it, like this is going to be 1/2 x to the fourth, I don't know, let's say plus 1. Right? And then we could say, well, instead of adding 1, why not add 2? This is getting a little messy here. And this is 1/2 x to the fourth plus 2. And, if we add negative numbers, well, that just looks like this. 1/2 x to the fourth minus 1, say. Right? So all of these functions should look identical. But all of these functions here, it's the same graph, just translated upward or downward, right? So, at the various x values, the slopes of these functions are exactly the same. It doesn't matter how high up you translate it, how low down you translate it. At, at this x value right here, whatever this is, the slope here, here, and here. It doesn't quite look like it from my drawing, but the slopes at each of these points on each of these graphs here should be exactly the same, right? So we're kind of saying, for all of these functions here, they all have this same slope, 2x cubed. Right? Okay.